Hi, welcome to our final presentation on the analysis and redesign of an automatic vegetable peeler. Project description is the vegetable peeler removes the skin in an efficient and non-wasteful way from an assortment of vegetables. The vegetables attached to the sharp lower grip spun by a motor and a sharp upper grip that is free that spins around the vertical axis. The blades are placed on opposite corners to lightly engage the vegetable surface, and they're moved up and down by a motor to cut the vegetable. The production volume is estimated to be between 50,000 and 200,000 per year. The target customers, the primary customer is commercial kitchens or manufacturing plants, so where it's necessary to peel large amounts of food in an efficient manner. So like when you have a large amount of customers in a restaurant. And the secondary group is personal kitchens, so places where convenience of an automatic process is desired, but not necessary for food prep.
We've broken down our model of the peeler into 18 individual parts and sub-assemblies, each labeled with the quantity needed in the system is provided. On the right-hand side is an image of an exploded view of our CAD model with callouts for each part and sub-assembly, which are circled in red.
This is our functional analysis system technique diagram, or FAST diagram, where we've categorized the main functive, which is to peel vegetables, into a series of increasingly specific ones as shown. And this is our function component mapping matrix, where we've taken each individual component of our design and assigned them each to a variety of functions seen in the first row. Here you can see that the most critical functions are on the right highlighted in green, and the most critical components are the motor, the blade, and the pillar stand in view.
Here's our quad chart classification. So on the bottom right in the high cost and high importance are the parts that are most ripe for redesign for manufacturing and for assembly.
Moving to the product family design, we have the functional differentiation table that lists down the functions of the product that are similar and different for both the groups, which is based on the use of the customers. Moving to the component commonality table, we have the components that are common for both the groups listed under platforms and different for the groups. They are listed under modules.
We've created two different modules of the CAD for a primary and secondary use case. The primary module features a longer top pillar for larger vegetables, as well as a three-pronged grabber and end grabber for increased food stability, all suited for commercial use. The secondary module has a shorter top pillar and single-pronged end grabber, which is ideal for a home setting and smaller vegetables. Between the two modules, the interfaces between the linear motion shafts, lead screws, slider supports, top plate, and lead screw end caps will remain the same, despite the overall differences between the two. These are the product family analysis diagrams for both the original and modified assembly sequences. Note that the redesign branches 6 steps later than the original.
Here's our manual assembly time chart. And we have very large assembly times for the parts associated with the slider assembly and stepper motor assembly. So to target this, we have chosen the slider assembly to redesign as the module part and the stepper motor mount to redesign as the platform part due to their high assembly cost, high product importance, and their critical functives on the FCMM. So for the slider assembly, we chose to merge the slider plate into one of the subparts on the slider assembly. And this helped us reduce the number of parts, and we also simultaneously reduced the number of fasteners and increased part symmetry. And for the stepper motor mount, we again combined it with one of the lead screw end caps and reduced fasteners and increased part symmetry. So overall, we were able to achieve an 18% decrease in total manual assembly time and a 14% increase in manual assembly time efficiency, simultaneously not affecting the product function, and we were able to eliminate 2 parts from the entire assembly. The only negative effect is that we might require more complex molds for die-casted parts or injection molded parts.
So for designing for automated assembly, we chose a subassembly containing the slider supports, bearing, and lead screw end cap due to the slider support's high assembly cost and the corresponding parts that really combine the three. The total handling and insertion cost for this subassembly was calculated to be $5.67. For our redesign, we increased part symmetry, added features to facilitate orientation, and adjusted our parts to avoid tangling and nesting, as shown in the before and after images. And after our redesign, the total handling and insertion cost was $5.49 per subassembly, which was an 18-cent cost savings. This positively reflected less material removed from the slider support during the machining, but possibly negatively, the end cap had a more complex shape, which could potentially add cost depending on process selection. The overall product function is unaffected by this.
So with the process selection parts, we chose part 13 and part 15A being the slider plates and the slider supports. Overall, the most critical dimensions for both of them were the dimensions in between the holes, as this goes for alignment and providing structure for adjusting to position and providing structure as per our FCMM. So for part 13, we decided a tolerance of 0.3 millimeters was adequate, and for part 15A, a tolerance of 0.2 millimeters. In running through process selection for part 13 and 15A, we decided on the material of aluminum. For part 13, the candidate process were die casting, centrifugal casting, machining, with the selected process being die casting. And for part 15A, the only candidate process was machining, which was the final selected process.
For design for manufacturing, we redesigned the slider plate using die casting method. The total cost per part before redesigning was $1.44. The cost per part after redesigning was $1.37. The total cost per part was reduced by 4.71%, and there is no significant impact on the function and assembly cost per part. The DfM guidelines that were used are DFDC 2, 3, 4, 5, and 6. Here we see what we had done to redesign the part. For example, we had reduced the number of side pulls. We had also added the draft angles for easy removal of that, etc.
We then chose our top slider support to redesign for machining. The part is to be fabricated from aluminum 6061T6, and doing an analytical cost study of the original part, we found that the total cost per part was $6.38, with the majority of the cost coming from the machining cost. We then used DfM Pro to evaluate the flaws in our design from the machining process, as shown in the following two slides. We then redesigned our part for manufacturing, resulting in a total cost of $4.09 using the analytical method. We were able to reduce the cost per part by roughly 36% without any significant impact on the function and assembly costs after the redesign. We primarily used DFMC5, DFMC9, and DFMC15 to inform our design decisions. Overall, the changes can be summarized as a reduction in complex and impossible features, paired with the use of tapped holes to further decrease processing steps. We were also able to consolidate the top and bottom slider supports into one part, reducing the overall number of differentiated parts in the assembly. Lastly, we used hubs and found the cost for both the before and after design for batch quantities of 50, 100, and 200 parts, before extrapolating to our 200,000 batch count. Here, we notice the same trend of our redesigned part being cheaper to manufacture by machining, but there is quite a large gap between the hub's estimate and our analytical estimation. We believe this may be due to our small part size.
Providing a product service system will increase the customer experience with the product. We will provide preventative maintenance and repair services at increments of 10,000 vegetables. This will help prevent breakdowns and ensure no time is wasted during food preparation. It will also reduce the repair costs as repairs will be much less frequent. By providing maintenance to the product, any additional environmental impacts caused by improper functionality can be reduced. And additionally, not as many parts will need disposal. The benefit of our redesigned system is a total cost reduction of $9.66 per assembly by a simpler manufacturing and assembly. Additionally, a pro of this redesign is that we greatly reduce the number of parts and decrease assembly and handling time. However, in some cases, there was only one viable manufacturing process for a part. A different approach could be redefining thresholds of what is considered a high-cost part in the quad chart, apart from those purchased by OEMs.